start. Good afternoon, everyone. Shall we start the session? A quick statistic. So you expect a lengthy hair for a female and not presence of moustache. Okay. So not presence of moustache with a short hair or a lengthy hair to some extent may fit for male as well. Okay. These things you call it as a confusion. Okay. So you need to clearly draw a line. Okay. Or you need to clear on this, you are supposed to draw a surface or a line. Okay. So one side of the line will be one category, another side of the line will be another category. So you have two different categories. I am starting with a 2-class problem, we can extend this for multi-class problem as well. Okay. So right now I am interested in your male or female, just 2 classes are available, 2 features are available. With this I am actually proceeding. Is it clear? Is the problem clear for you? Now if you want to distinguish the surface, or if you want to distinguish the 2 different categories or the classes, okay, if you are drawing a line for it, it falls under the category of linear classifier. Okay. So if you are not drawing a line, if you are drawing a circle, or if you are drawing an ellipse, or if you do any other higher dimension one, it falls under the non-linear one. Okay. So or you require multiple lines. If it is not possible with a single line, if you require multiple lines, even that is falling under the non-linear category. Okay. So with this understanding, we will be restricting our discussions on the linear discriminant analysis. How do I decide on this line? Okay. How do I draw this line to distinguish the 2 category? Okay. So this will be your prime area for this discussion. Okay. This
அந்த விண்டோல கிளிக் பண்ணிட்டேன்.
Okay. Okay. So just like an example that we have considered, this is a standard example that will be given any pattern recognition book. Okay. So they wanted to discuss differentiate 2 different fishes. Okay. So based on that 2 different fishes, they have actually identified the salmon and bass. These are the 2 categories of fishes, and those 2 categories are indicated in 2 different colors. Okay. So the line which you are going to draw is going to be the classifier. Okay. So this classifier should be able to identify the classes very clearly. Okay. So everything that is lying on one side should be of one category, on the other side should be on the other category. So according to us, if we draw a line, okay, based on the 2 features, the 2 features, one is there on the x-axis, which is going to be the length of the line, presence of moustache could be on the y-axis. Okay, 2 different features I have taken for the visualization. So if it is multiple features, then visualization becomes difficult. That's why I have taken 2 features. Okay. So one feature along the x-axis, another feature along the y-axis. Based on that, you have plotted the points. Okay. So many students, each person will have his own, the length of the hair and the presence of moustache is going to be different for every person. So those each data becomes your sample points or the data. Okay. So these data you are going to plot it and you are going to get it like this. Okay. Something like this. So you can consider like all the red points could be men and all the green points could be women. Okay. So now you are supposed to draw a line between these 2 classes, so that all the people or the points who are lying on one side is going to be male, on the other side should be the female. That is the basic idea that you have to do. Okay. So this is actually how do I draw this line? How do I say that the classifier is good or bad? Okay. So classifier is good means I should be able to classify it correctly. So given the length of the hair and the presence of the moustache, I should be very clearly able to say that he is a male or a female. Okay. So if you are able to do that correctly, then your classifier has a very good performance. Okay. Or in other words, your boundary is going to be very good. Okay. So putting the boundary in a correct position is what the entire job of your classifier. How exactly you are going to tweak this parameter so that the boundary becomes correct. So that is what you need to understand. Okay. So this is an example for a good boundary and this is an example for bad boundary. Why? Because on this side if you consider everybody is female and on this side everybody is male. So all the green points who are coming on this side are misclassified, okay. They are not classified correctly, okay. They are incorrectly classified into another category, okay. So the number of points that are lying on the other side or the misclassified is more, or in other words the accuracy is going to be less, okay. So because the accuracy is less, you cannot call this boundary as a good boundary, okay. Or in other words, if you are going for this particular category, if you look at it, you just have only one red point that is on the other side. So red is on the side, okay. All the side should be red color, belongs to male, and all the side should be female. So with that classification, if you draw a line, only one particular person gets misclassified, okay. So this is actually acceptable to some extent, okay. If you are able to perfectly classify, it is fine, but perfectly classification also has some drawbacks. We will discuss about it later, okay. Shall I say next so that you can click? Okay. So now you will have to express this in terms of a mathematical function. We will have to always start with a mathematical function. So what are we going to do? We are going to specify a feature vector. So this feature vector I am going to call it as x, okay. So this x is what you have considered like length of the hair and the presence of moustache. Each and every field, okay, each and every feature you are going to put it in the form of a vector. So that vector you call it as a feature vector. So that is nothing but your x, sorry, that is nothing but your x that is present over here. So what you will have to do, you will have to find out, now you are trying to assign some weights, okay. So what are these weights? Weights is nothing but the w that is represented in this formula. Would this weight should be arranged in such a way that, okay, once I give the new value, it has to compute and clearly say me whether it is belonging to one class or the other, okay. So these weights are the ones which you are going to do in, it is going to be different for different classifiers, okay. So how do we decide on this weights, okay. So once you have assigned the correct weights, then your classifier is done, your classification job is done. Then you will have to just give your new input x and then test out whether it is giving you the correct result or not, okay. So that is all you will have to do. So this entire thing, if you represent in the form of a picture, you can specify that this is going to be the line, okay, or this g of x is represented in the form of a function which is a combination of this weight and the feature vector, okay. When you multiply both, you are supposed to get, this is nothing but a linear form, right. It's almost a line, or in other words, in a hyperdimensional, it is in a linear fashion you are representing it. So if you represent this in the form of a line, one side of it should be equal to one category, other side should be the other category. So if you represent this line, so any point that is lying on this line will satisfy the equation basically, okay. So if g of x is equal to 0, you will not be able to say to which category it belongs to, or it lies on the boundary, okay. So anything it is greater than 0, okay. So this line is 0 means one should be less than 0, other side should be greater than 0. So you are able to convert this classifier problem into a mathematical formula, okay. So once you have this g of x greater than 0, you are going to say that it is belonging to class 1. When it is less than 0, you are going to call it as a class 2, okay. Now what is the importance? So that is what you have given over here. So the entire definition of your classifier has now been converted into a mathematical formula which is a linear fashion, okay. So ultimately you know the value of x, only thing is you will have to find what the value of w will be, okay. So if you are able to get the value of w, your classification job is done. Is it clear? Fine. Now, so an example for the hyperplane, why do we specify the classifier boundary as a hyperplane is, see, when the number of dimensions is increasing, then it is going to be based on the dimensions we can actually classify the hyperplane, okay. Suppose if you are just going to have a one-dimensional one, suppose in our example we are going to consider only the length of the hair, okay. So if the length of the hair, if it is going to be plotted, then it is going to be a one-dimensional one, okay. I have only one feature that is left out. So you literally have one dimension there where the length is going to be, x value is increasing over here, okay. This is 5 centimeter, 12 centimeter, like this. You can actually plot the values. So this may be corresponding to one person, this may be corresponding to male, female, like that. You may have a set of values, okay. So on the closer side, you will have for male. So if you draw a line over here, or if you put a point over here, there is no need of line for you. So if you put a point or a simple threshold, anything greater than that threshold is going to be one category, anything less than that threshold is going to be another category. So your entire hyperplane or your classifier is now reduced to a point, okay. So if provided this is one dimensional, but if it is extended for two dimensional, then it is going to be a line, okay. So if it is going to be three dimensional, it is going to be a plane, likewise, okay. So in general, we are representing it in the form of a hyperplane. Is it clear? So if you represent in generally like this, so you have a hyperplane, this is going to be a classifier, anything lower than this, below this will be one category, anything on the other side or the above side of this is going to be the other category for the two class problem, okay. Now, so this is what I have represented. Now what does this W represent? How do I understand this W, okay. So when you are representing this W, you need to understand, what each and every term means over here. So each and every feature you are going to associate a weight, right. So this weight will totally decide on the orientation of your line, okay. So the orientation of the line will be decided by whatever weight that you are having with, okay. So what happens to W naught? W naught will be nothing but the distance from the origin, okay. So it is, see, this is what you call it as the intercept, right, in a linear fashion. So intercept is how much it is far away from the x axis or y axis or the origin point. This is what we specify. So here with respect to this line I am measuring, so W naught will be nothing but the distance away from the origin, or in other words, the positioning of your line will be controlled by W naught, and the orientation, okay, the tilt, okay, whether it should be vertical, horizontal, what slope it should have, that slope is nothing but your Wt. That is from your linear equation, y is equal to mx plus c, right. M decides the slope, slope is nothing but your orientation. Orientation will be how you will have to tilt your line, okay. So the constant c will, or the W naught will decide on how much distance, where exactly it has to be placed. So if you are able to decide and finalize these two parameters, you are able to decide the classifier, okay. So in the previous sessions, you might have learnt about various optimizations that is going on in ML. So what are the various optimizations you have, techniques you have learned? Name any one optimization technique. Gradient descent method, okay. What do you do in this gradient descent method? So initially one method, okay, so ultimately you need to find out only this W, right. So why don't I assume some random value for the W and then I train on something? That's also possible, right. So that's what you're doing in most of your training in your ANN or other network. You do some training where you try to find out this W, okay. So you initialize with some random values and then you use this gradient descendant method to converge to your final solution, okay. So once you got the final solution or to the correct value, when it is minimum, when the error is minimum, you are sure that this classifier will perform very well, and you give that as your output. On that output is nothing but the line with the perfect weight. Is it clear? So ultimately, what is your job now? We'll have to find out the line. So the line includes the orientation as well as the distance from the origin. Once these two are fixed, you are done, okay. So now if you are not able to do it in a random way, okay, there are many methods for doing it, okay. So one procedure is what you are told about the optimization, that is gradient descendant method, okay. You start with random weights, use the gradient descendant method, converge to a lower value and then get it done. So there are other methodologies also to decide on the W, okay. So what are the other methodologies available, okay. So just an example, so you have a weight, okay. So this is the bias weight and these are your features, x1, x2, x3, etc. are the features. So normally when we are trying to do this classification job, we are so fond of the matrices, okay. So what we will try to do is we will try to convert everything into form of a matrix. So to convert into a matrix, what I am trying to do over here, this bias, okay, a constant was available, right. So that constant also you are trying to bring in as a feature, okay. So when you try to bring that also as a feature, the constant has to be multiplied with 1, okay. So the value will be this something like x1, x2, x3, you have d features, totally d features are there, and additional you have one more constant, and each one of them will be having a weight, okay. So these weights will be multiplied with this x, okay, and when you add up all these two and then you put a threshold, finally you will get a category as category A or category B, okay. So this threshold will decide greater than 0 or less than 0, so that will be your classifier, okay. So now you have converted the classification problem into a mathematical one, fine, okay. So to go more into the details, okay, so whenever you are trying to write the matrix including the bias as a new weight, okay, you call that feature vector as augmented feature vector, okay. And okay, let me go for the previous example, okay. Suppose if I am going to have this particular class category, okay, so what all possible errors can happen, okay. How will you classify? So what are the different possibilities? I can have a green on the other side, on the red side, I can have a red on the green side, a green on a green side, red on a red side, right. All these 4 possible combinations are there, okay. So which of the 4 combinations are correct, which of the 4 combinations are incorrect, okay. So I can have, assume this boundary is available to you, okay. So on the lower side you have green, on the upper side you have red, that is the correct classification, okay. So if a new point comes which is actually a red, if it falls in this category it is a correct one, if it falls over here it is a wrong classification. So for the red point itself there is a 2 combination you have. Likewise if a green point comes over here it can fall either here or there, okay. So that again has 2 combinations, totally you have 4 combinations. So among this 1, 2 are error, among the 4 2 are error, 2 are correct, okay. So how do I differentiate the 4? I need some sort of values. See, ultimately what you are going to check is when the weight g of x is nothing but your classifier, when that classifier is giving you a positive value you are going to say that it is going to belong to class 1. When it is going to give you a negative value, you are going to say that it is belonging to class 2, done. How do you identify the error here? Yes? Bias is also a part of your weight, okay. So bias has nothing to do with the identifying the wrong output. How do I identify the correct and wrong one? See, all these are actually conditions, right. So I have put a condition, if the actual class is, it's a green dot appearing on the red side, it is a wrong classification. If it is a red dot appearing on the green side, it is a wrong classification. I cannot put an if and else condition to execute your code. I need a mathematical formula, okay. To do this, you actually go in for the another technique where, yeah. So this is the augmented feature vector. So the augmented feature vector you call it as y, okay, which includes the bias as well. So the initial bias you always take it as 1. So W naught will be the corresponding bias, okay. So this is what you do for the correction, okay. So what I want to do, I want to bring both the classes on the positive side, okay. I want to bring the correct classes on the positive side, and whatever negative value I am going to get, I am going to call it as an error. Are you able to understand? So what I am trying to do over here, I need a mathematical formula. Earlier you have decided a mathematical formula or a line on which if g of x is greater than 0, it is going to be class 1, less than 0, it is going to be class 2. That was your earlier definition. You need to modify that definition in such a way that, okay, so if it is greater than 0, it is correct class, okay, whether it is positive class 1 or class 2, it is correct. If it is less than 0, it is going to be an error. It is easy for us to identify that, right, okay. So how do we convert that? So what we are trying to do over here, we know that anything greater than 0 is going to be a positive value. Positive value you have called it as class 1, right? Anything less than 0 is actually a negative value. Negative value you made it as class 2, right? So class 2, class 1 and class 2 you are going to represent as plus 1 and minus 1, okay? So plus 1 will be class 1, minus 1 will be class 2, okay? So if I am going to multiply g of x with the minus 1, what will happen? I will get a net value as positive. A negative class getting a negative value is correct for me. So in that sense I am performing a normalization. This process you call it as a normalization, okay? So what you are trying to do over here, you perform some sort of normalization, or in other words, normalization is nothing over here. You just need to multiply the negative value with the corresponding weight if it is class 2, that is it, okay? So once you do this normalization, how your problem gets converted to, this is how it gets converted to. Earlier, one side of the class is class 1, this side of this is class 2. Now, this is the first quadrant where both of them are positive, this is the third quadrant where both of them are negative. Weights are negative and then the class is also negative. But you are able to bring them on both on the same side of the plane, hyperplane or your classifier, okay? So that's the advantage you have here. So anything on this side which is going to be the positive, it's correct, okay? Anything which is lying on this side which is negative, it's going to be incorrect. I don't bother about whether red is getting classified as green or green is getting classified as red, I am not bothered, okay? So anything is negative is going to be your wrong classification, anything which is positive is going to be a correct classification. This will actually help us in correcting the values, okay? Even when in the trial and error basis you do it, right? Whenever you try something, when you get an error, you try to correct it by some adjustment. So we need to identify this error. So this, when you give such a representation, it becomes very easy for you to identify the error and correct it. Is it clear? Fine. So what is your ultimate aim? So once you are given a set of features, you are supposed to identify the weights. So the weights you have converted into an augmented feature and also you have normalized one, okay? So normalized in the sense a negative, if it is belonging to class 2, you will multiply it with minus 1, if it is belonging to class 1, you will multiply it with plus 1, that is it, okay? So that with that value you give it as a feed as an input, and if you get the net result as positive, it is correct. If you get a net result as negative, it is error. So if it is an error, you will have to update your weights, okay? You will have to change your weights in such a way that you always get a positive value. When you always get a positive value, you got the accuracy to be perfect, okay? So that's what your aim is. Is it clear? No. Fine. So all these training error, okay, so all these you are now training on, I mean you are performing, you are doing this classification based on some set of input data. We normally call them as a training data, okay. So with this set of training data, you are trying to draw the line, and if you get an error which is 0, your training error is 0, okay. Your training with your input data sample, it is perfect, okay. So then you can go in for the testing. So testing error and training error, we normally keep it as two different categories. Okay. Fine. So this is an example that is given. So here you can see that this is belonging, all the green squares are class 1 or the blue circles are class 2. So where exactly can I draw the line? That's the question now, okay. So I can draw a line which is starting from this edge, okay, up to this edge, okay, sorry, it cannot go up to that, it can go up to this, right, okay. So or anywhere if I am drawing the line over here, all those are valuable or possible correct classifiers, and it will give a 0 training error, okay. So this space you call it as a solution space. It's not just one line that is getting satisfied, you have multiple lines that are satisfying the criteria. Okay. So when multiple lines are satisfying the criteria, you can take any one of them. That's what it means. Okay. Your ultimate aim for the classifier is to get any one solution in the solution space. Okay. Any one solution. It is not that this should be the one. We are actually looking for any one solution in the solution space. Okay. So any line that is lying like this or this purple line, all these are valid classifiers or correct classifiers, which will give you a training error as 0. Is it clear? Now, so the solution space or the solution region is highlighted over here, okay, and then this will be the best solution I can get where a training error will be 0. Okay. Okay. Yes. So these are the net things. So possible things I am actually giving you. So this is the first classifier. This is another classifier. Okay. The same classifier is trying to reorient itself. So you are trying to find out whether which one is performing in a better sense. This is just for you to identify. So many lines it is possible for you to draw. Okay. So how do I say that my classifier, which line should I choose? I need some sort of criteria on this, right? So, and I also need to know whether I am getting the correct classifier. So for these two, you need some sort of criteria or the parameter. Okay. So these criteria, based on the decisions you are going to take, you can actually follow a mean square error procedure, or you can use a Fisher's classifier, you can use a PCA classifier. Okay. Each one of them adopt their own strategy. Sorry, can you put that on silence? Excuse me. Okay. So now what you are trying to do over here, we are trying to find out the value. A criteria needs to be there. Okay. So this criteria should be decided in such a way that your weights are correctly assigned. So what is your W? W is your orientation. Orientation should be correct, and also distance from the origin also should be made correct. Distance from the origin is your W naught. Okay. So these two decision has to be done correctly. For that you require a criteria. So what is the criteria you can choose? You can choose a mean square error procedure. So what am I trying to do? So I have a set of points. Okay. So in this, can I just? Okay, never mind. Okay. Where else I'll go for this? What do you mean by a dot product? W into x. Okay. Suppose if I am performing a dot product between the two vectors, what is the meaning or verbal meaning that you can give for the dot product? It's nothing but the projection on a particular line, right? Okay. So suppose if you are actually performing a W dot x, it means you are trying to project the feature vector onto the W. W is your classifier. Okay. So you are trying to project the points onto a classifier. Suppose if this is the classifier that I am trying to do over here, you have certain data points that are available. Okay. So these points, when you are trying to project over here, okay, so this can also be measured as a distance, right? So these projections are nothing but the distance. Okay. So I should draw the line in such a way that the error or the distance from this particular point to this classifier should be minimum. So that's what you mean by minimum squared error procedure. Okay. So you will have to adjust this x in such a way that the error from this point to the classifier should be minimum. Okay. Suppose according to you, we have actually put on the same side normalized one. Okay. So this is for the unnormalized case. Unnormalized case in the sense you have another category on the other side. Suppose if you have this category also over here, I am actually trying to project these points in such a way that this will be the distance from here, right? Okay. Suppose if I have another point over here and another x that is present over here, what will be the error? All these will be negative. These are going to be a positive. Okay. So, this will be the error that I am going to get for with respect to this data point, and with respect to this point, this will be the error. Okay. The length or the distance from this point to the projection, or the projection value on your W, this is the W, okay, that will be the error for this parameter as well as this parameter. So, when I take this error, when I sum it up, square and then sum it up, then that total error should be minimum. Okay. So, if the total error is minimum, you can be satisfied with whatever W you have with you. That is your ultimate idea of doing this. Okay. So, you are now trying to minimize it. You choose the values in such a way that you are trying to minimize the errors. I am not going into the derivations. I know that it is afternoon. If I start the derivation, everybody will lose track. So, I am skipping off the derivation. I am just giving you the net essence. If you are interested, you can definitely go and derive it. Okay. So, you will have to have a criteria function which you call it as J. Okay. So, which will have the squared error, and that has to be minimized. Minimized means you will have to perform a derivation and finally come up with a solution. Okay. Fine. I thought I will take an example with this least square method so that it becomes easy for you. Totally D features are available. Okay. So, among that, the first feature is always your bias. Okay. So, you have represented that entire vector or the data points into a matrix form now. Okay. So, once you have represented this as a matrix form, you have a A. Okay. So, A is nothing but your you are trying to convert this into the linear system of equations. Okay. So, this is your expected class. Okay. So, when you are trying to solve for A, you will actually get the W that is expected. Okay. Okay. So, ultimately what you are trying to do over here, let me take an example. So, we call the system as an overdetermined system. Why? Because you have more data points, okay, than the actual number of dimensions. So, it is possible to have more than one solution. That is what I want to link. This is how I am linking the solution space with your max. Okay. So, since it is overdetermined, definitely you will have more than one solution, and this is the error that you are calculating over here. Ya is the calculated one, B is the actual one. Okay. So, this is the correct output, and this Ya is the calculated output. So, an error is nothing but a difference between the two, that is taken as E. So, this is with respect to one particular one. When you add up everything, this will be your criteria function that you have. Okay. So, you need this squared error to be minimum. Okay. So, this is the error, square it, try to minimize it, that will be your criteria. So, when that error is minimum, take the W, that is it. A simple solution will be a pseudo inverse problem where you are trying to get y inverse, yt will be nothing but your expected A. Okay. So, let us take an example. Yeah. So, I have 2 points. Okay. So, 4 points in total, 2 data points, that is red points belong to one category and blue points belong to another class. Okay. So, their coordinates are given. So, these coordinates are nothing but the feature 1 value is 6, feature 2 value is 9. Okay. So, 2 dimensional, it is represented in the form of a 2 dimensional one. So, these 4 points are given to you. Now, you are supposed to convert these 4 points into a matrix. Okay. So, this matrix you will have to augment with first value. Okay. First value is nothing but your bias. Okay. So, bias by default you take it as 1 for positive class, for an -1 for the negative class. Okay. This -1 is for the class 2. Okay. So, all these are made as normalized. So, I am normalizing it by converting this 5 9 as -5 -9. Okay. This 0 4 as -4. Okay. So, this belongs to the second class, this belongs to the first, this also belongs to second class, these two belongs to the first class. So, when you put everything put together, you got this Y matrix. Okay. So, when you have this Y matrix, what is your expected output? I need my output always to be 1, that will be my correct class. Okay. So incorrect class will give me an output as -1. I told you when you put on the normalization, anything you are getting it as positive is correct. Anything you are getting it as negative is going to be incorrect. So your expected output is everything should be, this is your actual output, not expected output, this is your actual output, everything as 1. Okay. So now you will have to find A is nothing but your weight matrix. So this matrix you will have to get in such a way that y into A should be equal to B. Y is your input data, which is x. Okay. Now convert it to y. This A is your line parameter. Okay. So when you have this line parameter, you are here it is, you are taking it in a direct fashion. Okay. So it is available. So y backslash b pseudo inverse, it is possible for you to take an inverse. So when you take an inverse, you got the value of A as these. Okay. So this, what is your first parameter over here? Yes, A is an approximation of this. Okay. So there are, you cannot have an exact solution, it is only an approximation. Okay. So there is a possibility for you to get a training error as well. Okay. So here it is possible for you to get a training error to be 0. Okay. So when you project it back, you can see that for any A, so with this value as A, for every y value that you have over here, if you multiply it, you will definitely get a positive value. Every class you got the output as positive, which means your classifier is correct. Okay. So the same thing if you try it for another example. Okay. So from over here 6957, these are the two values that you have over here. So this, when you keenly look at this, where exactly the points will be falling. So this is your first class, this is your second class, I mean not second class, class 1, second one. Okay, this is the first data point 69 represented in the form of an augmented one, second data point of class 1 57 represented in the augmented fashion, and this will be the class 2 values. Okay. So for this you are converting into a matrix Y. Okay, and then just like the previous one, all your actual output should be 1, and then you calculated the weight matrix over here. Okay. So with this weight matrix, when you multiply it back with each of the y value, y1, y2, y3 and y4, each y value if you multiply it, you got an output something similar to this. Okay. So this line, whatever line parameters you had here, that is the purple line that is being drawn here. Okay. So those are the parameters. So once you get this, you can see that one particular thing is appearing as negative. Which one? The third data point. Okay. So the third data point corresponds to this red square. It's actually misclassified. You are supposed to get everything as positive. If you are getting everything as positive, your classification is correct. Now you got it as wrong. Now what is the problem? Why do I get such thing? Is it not linearly separable? Linearly separable in the sense, if you draw a line, I am able to differentiate them into two different categories. Is it linearly separable? Yes. Then what is the drawback that is occurring over here? Whenever you go for the minimum squared error, always the outliers will influence a lot. Okay. So this outlier will try to pull the line, okay, based on the presence. Okay. So because the outlier that is present over here, okay, it influences the line to be pushed towards it. That's why it comes over here. Okay. So because of that, this red square got misclassified. Okay. So that's actually a drawback you have in minimum square or squared error procedures. All the squared error procedures will be affected by your outliers. So if you have one particular point which is very far away, which will definitely affect your line that is present. Okay. So what exactly you are trying to do over here? The distance from this one, okay, the squared error or the squared distance from here is matching the squared distance of sum of the squared distance of all these points. If you can see that this is one point, this is another point. Okay. So this will have the matching point. This blue circle will pull the purple line towards it, and this red square will pull the line to it. Okay, based on your square error. So somewhere it comes and settle down here. So this is why this is the error that you are getting over here. Is it clear? Fine. So how do we rectify it? So for rectification, do I have it? Yeah. So this is what you are typically trying to do over here, okay. So this is for a PCA, but it can be taken for this as well. So PCA also is a kind of identifying, getting the value of the classifier, okay. So the W matrix. The only thing is you are trying to reduce the dimension, okay. So when you are trying to reduce the dimension, when you have 2 dimension, ultimately it has to be reduced to 1 dimension, okay. So you can see that, this is actually, all these points are plotted in a 2-dimensional x1 and x2. So when you are performing a projection is nothing but your dot product with your weight matrix, okay. The feature vector dot product with your weight matrix, you are performing a projection. So all these projection is now done on one single line. So you have now reduced to a 1-dimensional one. So in this 1-dimensional one, you can see that it is not possible for you to put a point to clearly segment the red line with the blue points. Red points and the blue points cannot be clearly distinguished by keeping a single dot, okay. So that's actually a drawback over here. But if you actually draw a line over here, so if you draw a line like this, all these are the projection points, okay. So when you perform the projections onto this particular line, now if it is easy for me to put a dot over here, I can say that anything towards this side is red, anything above this is actually blue. Clear classification is possible if I project onto this line, okay. So this projection, how do I classify it? Another category it comes in. What you are trying to do over here, you are trying to find out the mean value, okay. So if you take this as category 1, what is the mean value of this category, okay. So mean value will be somewhere over here. Likewise, you calculate a mean value for all the blue points, that will be somewhere over here. You try to find out a difference between the mean value, okay. So what is exactly you are trying to do over here? Why do I need to calculate this mean, etc.? See, what is your ultimate aim? So if you want to if you want to identify a man as a man or a girl, okay. So what exactly you are requiring? You want the length of the hair for all the men to be similar, right, or to be close enough, okay. And all the length of the hair of a man from a female should be very much far away. It should be very much distinct from each other. Or in other words, if I calculate the mean value of hair length for a man, okay, and it is going to be some value, right. So that value should be very much different from the mean value of hair length of a woman. That is what you are trying to distinguish. If you are able to get that, then that is a very good classifier, right. So that is why you are going in for the mean value. What I am trying to do over here, I am trying to look for a point where the mean of the 2 classes is far away, okay. So if it is very far away, it is easy for me to put a point in between, okay. If it is very close, then it is very difficult for you to fix on the point. That is very simple. So based on this category, you are actually putting this criteria. What is your criteria now? This is your J is your criteria. As I told you, for squared error you have a criteria, and this is another criteria you are taking. What you are trying to take over here? You are trying to keep the mean of the 2 different classes as far as possible, okay. So you are trying to differentiate the difference between the 2, okay. Difference between the 2 mean value becomes your criteria, okay. And not only mean, just if you take a mean value, you have a drawback or a disadvantage over here. So what happens, all this red ellipse belongs to one category, blue ellipse belongs to class 2, okay. So if you calculate the mean value, mu1 this one and mu2 is this one. So if I project this mu1 onto the x-axis and this mu2 onto the x-axis, the difference between the 2 mean value on the x-axis is larger, whereas the difference between if you project the mean value onto the y-axis, it is smaller. So what is your expected one? I want a large difference on the mean. So what you will do, you will try to project all the values onto x-axis rather than onto the y-axis. So what exactly happens? There is a overlap. You can see that this particular point exactly overlaps with the other 2 category. So this is not just looking at the mean. If you look at it, it will actually deceive you. So what you are trying to do over here, you are adding one more dimension, which is the scatter. Scatter is nothing but your variance, okay. So this is how max comes into picture. So you are trying to look at the mean value. So, within a class I want the mean value to be, I mean within the class the spread should be very much less, okay, and between the classes, if I am trying to take a two different class, the variation should be very high, okay. So, the variation is, I am actually classifying it as variance SI. So, for each class the variance SI will be nothing but you subtract the y value with the mean, okay, that becomes square it up, that is your variance, so your general variance formula. So, the variance of class I is SI square, class 1, class 2, so two different classes you have. So, between the two classes I should have a large variation, okay, and between the classes, within a class I want very small variation, okay. So, that is your expected character. So, what you try to do over here, between class variation comes to the denominator and within class variation should be comes to the numerator, or it is directly proportional. Based on the proportionality you are putting it in the numerator and the denominator, okay. So, if you look at these two parameters, you call that classifier as a Fisher's classifier or Fisher's linear discriminant function, okay. So, if you are using this function to find or finalize your W, okay, if you take this as your criteria and then you finalize your W vector or your classifier, then that will be your Fisher's classifier. You are classifying, you are using your classification using the Fisher's linear discriminant function, okay, fine. So, this is the I have told you, so this is the variance. So, this is the variance of class 1 and this will be the variance of class 2, okay. So, all these variance I want it to be maximum, okay. So, this will be the direction. If you draw a direction, then based on that only you can have the final classifier, okay. So, you will have to finally optimize this particular thing to get your Fisher's. Okay, till now we were actually discussing about the single class, right? How do I extend it for multiple classes? Okay, so it is not quite normal, we always try to distinguish a man from a woman, but there are other categories where you have multiple classifications required. So, can you adopt this two class into a directly into a multiple class? Can you think of some methodologies? Suppose if I want to classify into 4 different categories or 3 different categories, what can I do? I have only binary classifiers. Binary classifiers in the sense, one will be able to say it is belonging to this class or other class. Let me assume like that, okay. Or you want to say it is belonging to the class, it is not belonging to the class. That is one classifier that is available to you, okay. So, with this alone, will you be able to, how will you be able to classify 3 different classes? Nested if else statement, okay. Any other? I have only one classifier, right, or a binary classifier is available. With that I had to extend it for the multiple class. So, what I can do, I can go for a methodology like this, okay. So, these are some of the methodologies. So, here this is one class, this is another class, this is a third class, 3 different classes are available, okay. So, what you are trying to do over here, you are trying to put how many classifiers? 3 classifiers are there, okay. H12 is a classifier which will say that one side of them belong to class 1, another side of them belong to class 2. Likewise, H13 will say that one side of them will belong to class 1, another side of them will belong to class 3. Likewise, H23 will say between the class 2 and class 3. So, with the 3 lines put together, you are able to achieve your final performance, okay. So, or a combination of more than one classifiers, that is what I am trying to say over here, okay. So, this is one classifier, classifier 2, classifier 3. So, a combination of these 3 classifiers can actually bring in the another classifier. So, the same thing can be extended for others as well. So, you can have various lines and then multiple category you can actually extend it to, but it is not quite short. It is actually you have other better strategies than going for a linear classifiers. This is actually a restriction for the linear classification, okay. So, linear classification has to draw a line and then identify to which class it belongs to. So, if you are trying to fit that for a general category, this is one of the methodology by which you can solve it, okay. So you can when you are executing your thesis or project, then you may be able to find out binary classifier. Okay, how can you use a binary classifier for a multi-class problem? All these talks about your 2-class problem extended to multi-class problem. Okay. Yeah, this is another example. Okay, I want to say one more thing. Okay, so how do I? There are blue dots belong to one category and red dots belong to another category. Okay, so can I use the linear classifier and segregate the 2 classes with just one line? Will I be able to segment that one side belongs to one class, another side belongs to another class? Is it possible for this particular category? No. Okay, wherever you draw the line, definitely you will have an error. Okay, so this is a typical example for non-linear class. Okay, so when it is non-linear, a simple example for a non-linear class, can anybody specify? Okay, your AND gate. Okay, if you plot your AND gate, your x1, y1, 2 parameters. Okay, so 0 belongs to one category, 1 belongs to another category. Okay, is it linear classifiable? What I am trying to do over here, you have a x1, x2. Okay, so when x1 and x2 are 0, it is 0. When x1 is 1 and x2 is 0, it is 0. And then x1 is x2 is 1 and x1 is 0, it is 0. Okay, and when both are 1, you have a 1 category. Okay, so all the zeros belong to one class, 1 is belonging to another class. Whether is this a linearly separable class? Yes. Okay, I can draw a line over here. I can say that one side of this belongs to one category, another side belongs to another category. Same thing for OR. When you draw OR, what will be? This is for AND, right? So OR, if you take it as OR, you will have an x over here, x over here, x over here, and a 0 over here. Okay, only thing, same thing, you can draw a line over here. Only thing is flipping. Okay, so here this side is 0, other positive side, greater than 0 is actually belonging to class 1, less than 0 belongs to class 0. Okay, whereas here less than 0 belongs to class 1, greater than 0 belongs to class 0. That is flipped. I'm sorry. That's actually flipped. Okay, so what could be another example for the non-linear? Both are linearly separable. Let me take an XOR. Okay, so what happens? You have a 0 here and a 0 here, a 1 here and a 1 here. Okay, when x1 is 1, this is x1, 0, this is 1. Okay, this is x2. This is actually an XOR problem. Can you draw a single line and then segment the 2? So this is a simple example. They normally take it for a non-linear classifier. Okay, so if you want to test your algorithm for a non-linear classifier, definitely they would have used XOR somehow. Okay, at least I require 2 lines to segment the 2 classes. It's not possible with a single class. Is it clear? Fine. So this is an example. Okay, likewise, if you, this is an example for non-separable classes. It is not possible for you to draw a line and separate the 2 different classes. Okay, that's it. Any questions? Had heavy lunch. I'm very, and you have given me all the mathematical formula, ma'am. We are not able to follow it. Right? Was it useful for you at least? Yes? Some basic concepts you are able to get it? Fine? Okay. I believe that whatever you learn, okay, you will have always mathematics just coming as a part. But unless you decode that mathematics into a understanding, it will be very difficult for you to proceed in your PhD. Okay. I hope I have decoded some of the mathematics that is present in the classifier. I do have an SVM session, but I don't think I will be able to complete within 5 minutes. So if it is possible, maybe I will take it in another session. It is left to you. If I have any queries, I will take it for 5 minutes, because 3:15 the next speaker will come. Any questions? Classifier and a regression. Okay, regression also you are trying to put, there again you have multiple regression, right? So regression, you are trying to fit a line for the data points. Okay. So you are trying to fit a line for the data points, and based on that, mostly we will try to predict. Okay. So the regression will be more or less used in a prediction part rather than for a classification part. Okay. So the same technique can be used for classifier as well as regression. Okay. So the minimum squared error can be used for regression as well. But the point is, you are trying to predict the next value. Given a x value, what will be x2 over there? You are predicting the value. But in classification, I am giving you x1 and x2. I am trying to find out to which side it belongs to. In that sense, it is different. That's it. 5 நிமிஷம் தான் இருக்கு, SVM முடிக்க முடியாது. Thank you. Thank you. Just a short introduction on SVM. Okay, we'll just have a, we'll not go into the mathematical details. I just want you to understand how it is happening. That's it. Can we go to the next slide? Yeah. Okay. Ultimately, you are trying to identify the plane. Okay. So I'm just skipping this. Okay. These are the various possibilities for an drawing a line. Okay. So how do I choose which one is correct? Okay. Fine. Let me start from here. Okay. So you're tending to draw a line over here. So that's what your linear discriminant function or a linear classifier does. So when you're trying to, if you're able to draw a line, you have a linear classifier, but it is not possible for you to draw just a line and separate the 2 points, right? So what you can do is, you can actually project this 2-dimensional one into a multi-dimensional, a higher dimensional one, into a 3-dimensional one, and then it is possible for you to segment. Okay. So when you project it, what you're trying to do over here, you're drawing this red hyperplane over here. On top of that, you have the blue points. Below that, you have a green points. So the conversion of this higher dimensional one, you call it as a kernel, SVM kernel. Okay. So depending on the kernel that you're going to decide, you will be able to convert into a higher dimensional one. Okay. So that you call it as a hyperplane. Okay. So here again, which one is the correct? Okay. So I told you there is a very large possibilities of your classifier. So how do you know which classifier will be the correct classifier? So SVM, what SVM does is, see, it actually tries to look for this BA. Okay. So what is the drawback of taking A classifier or B classifier? You have 3 different classifiers over here. B is one classifier which draws a line over here. This is another classifier. So among the 3, which do you feel that which is the best one? See, why? Because you have drawn this line based on the training. We do not know what the testing input will be. Suppose if you have drawn the B over here, suppose a blue star comes next close here, I'll be classifying that as a red dot. Okay, so that's actually a drawback for me. So can you avoid that situation? That's what SVM does. So what SVM does is, it simply takes the points, okay, so which are closer to your other category. Okay, so those points, data points, you call it as support vectors, because each data point you are going to represent in the form of a vector. The points which are close to the other class, you call it as a support vector. Okay, so using this support vector, you are trying to draw a line such that it is maximum far away between the 2 support vectors. So that's your ultimate aim in your SVM. Okay, so what you will try to do over here, yeah, you can see that, so this is the point. So this is the point closer to the other category, and this is point also is closer to this category. So if you draw a line over here, you can say that this line is very less when you compare to the distance from this one. Okay. So these are the support vectors. You have a support vector, star support vector, and a red circle support vector. From these 2 support vectors, this line has a maximum distance.
So you decide your line based on the maximum distance from the support vector. That's it. So that's how SVM works. Okay. Fine. Okay, so these are your support vectors which are very close, and based on these 3 support vectors you are drawing a line which is far away from the support vectors. So that will be the mathematics. If you go through the max, the entire mathematics will be like this. Okay, that's it. So this phi function, the phi is the kernel that I was talking about, which will actually convert from a lower dimension to a higher dimension one. Okay. Do I have an example for that? I don't know. Yeah, I forgot to mention about this overfitting. So if you're so comfortable in drawing a line exactly which gives you a training error as 0, which it may end up in a overfitting. Okay, you have drawn a line so flexibly in such a way that everything it is perfect, but maintaining this circle or a deformable shape, it is very difficult for you to draw the classifier. That's one drawback. It adds complexity. Apart from that, the error also is very high. Okay, it's so what is your ultimate aim? Ultimate aim, don't aim for a perfect 0 for training error. That's what it means. Okay, so there is, even if something is acceptable, if some small error is acceptable in training, to avoid this sort of overfitting. Okay. Yeah, this is the entire concept of SVM. Finally, you will have a equation like this. That's it.